The next MIT faculty speaker is Brian Anthony. Brian is Associate Director at MIT.nano, which is MIT Nanotechnology Center, and Director of Technical Operations at MIT Center for Clinical and Translational Research. Brian is leading expert in the design of intelligent and smart instrument and methodologies for monitoring, measuring, and controlling complex physical systems. His achievements include receiving an Emmy Award from the Academy of Television Arts and Sciences for technical innovation in broadcast engineering. Very impressive. Brian will talk about the autonomous factory, how data, digital twins, and real-time control are revolutionizing manufacturing. Please use Pigeonhole Live again for your questions, and join me welcoming Brian to the stage.
Hey, very good. Let's see, make sure this works. Go forward and backwards. Okay, very good. So first, I'd like to start by learning a little more about you. By a show of hands, how many of you have used ChatGPT, Gemini, or Copilot in your personal or professional lives? Okay. Have you used line fitting? So fit a curve to data in Excel, Google Sheets, looking at, say, your spending habits over time or from experimental data. So fit a curve to data. Okay, good. Have you tried to use ChatGPT to fit a curve to data? Okay, we got a couple hands. Okay. Have you tried to use a decision tree, a neural net, a support vector machine, or deep reinforcement learning to solve any problem of any sort? Okay, we got a couple hands. Okay, good. So I think one of the interesting things about ChatGPT is it's raised awareness to the massive population of opportunities with machine learning. And many of us now think, well, all machine learning is ChatGPT. And that's a mistake. So what I want to do today is talk a little bit about manufacturing. I'll tell you 3 stories about how we actually scale machine learning, how we deploy machine learning, and it's about bringing together both an understanding of the machine learning tools and the manufacturing. So I guess one other question before I get going. Anybody want to venture a definition of a digital twin? What is a digital twin? Anybody brave enough to say, hey, I can define what all the digital twins in the world are? So I'll give you my definition. There are many. I think if you asked 5 different experts, you get 7 different answers. A digital twin is a model. So as engineers and scientists and leaders, we've used models. We make models to predict the world, to predict the future. A digital twin, a model, becomes a digital twin once we use some data with some regularity to update the model such that the model maintains some similarity with a physical artifact. And that physical artifact could be a process, a product, a process. So the simplest definition, a digital twin is just a model that's updated regularly with time. So I want to talk about using models in the context of manufacturing. And when we talk about manufacturing, we talk about rate, quality, and cost, and predictability. We want to be able to get the same answer for asking the same question from our machine learning tools, which is not necessarily the case if you were to use something like a language model. But I look at the factory, the supply chain, the factory, not only as the vehicle with which we produce product at scale, but it's the vehicle with which we generate massive quantities of data that once we take that data and apply our insight, we can enable a whole slew of other beneficial value-add opportunities. We can gain real-time insight, we can do predictive maintenance, maybe we can do some increased visibility, better, faster decision-making. And so in this world of manufacturing, A lot of the things that we want to bring to bear to scale are not new. They're given new names. We call it digital twins instead of models that are updated. The proliferation of better AI tools, the cloud, somebody else's computer, and innovations in algorithms have allowed us to do more compute, get more data. But it's the data combined with context, combined with an understanding of the processes and things that we want to solve that allow us to be truly impactful. So one of the takeaway messages that we'll hear throughout, we're not replacing people, right? We need the expertise to know processes and machines and have context knowledge, and we need the data scientists to know, well, what are the interesting techniques? How do we get actionable information out of our data? Okay, so the 3 stories that I'll tell you about, increasing complexity. One, we'll start using a decision tree, a game of 20 questions and doing predictive maintenance. We'll look at engine manufacturing as well and how we use neural nets to predict the quality of an engine. And then finally, we'll talk about the extrusion of optical fiber, the 125 micron optical fiber that serves as the backbone to our wireless infrastructure of communication. And the technique that I'll end with that thing called deep reinforcement learning, we published a paper on this maybe 5 or 6 years ago now, and it's led to a lot of companies coming to us and say, hey, we read that paper about deep reinforcement learning for process control. We think we need that. And 2 years into the collaboration, after you say, yeah, that's great, we can explore, 2 years into the collaboration, we realized, actually, you just have not put into practice best practice of existing technologies. You don't need machine learning. You don't need advanced deep reinforcement learning. You actually you had some problems grounding your sensors. You had some problems with basic signal processing. You had some problems just getting the data registered from your processes with your maintenance. Right? So I'm all for the advanced techniques. Right? And if ChatGPT and the excitement around ChatGPT does nothing other than get you to use current tools in the best way that they can be, then it's a win. And then maybe in the next 10 years, ChatGPT will be at the point where it's old enough that we can think about the other ways to deploy it in manufacturing. So we'll talk about predominantly what I'll call these gray box digital twins, where it's a combination of some physical knowledge and some data. Black box if it's purely data-driven, and white box if it's purely algorithmic, but where we can really be successful is someplace in the middle. So IoT, smart manufacturing, Industry 4.0, it's all in some sense applied measurement and simulation science. To put it into the context for those of you that are in manufacturing, I should have asked that question. Those of you who are in manufacturing in some way, okay, we get some hands. So classically, the way that I'll call machine learning in the practice of on the factory floor, in your factory, you'll have on the one hand a type of machine learning called real-time feedback control, where we have some process, measuring that process, the temperature. An example would be baking. You want to maintain the temperature while you bake a cake. So you have a temperature sensor that monitors the temperature. If the temperature starts to deviate from what you want the temperature to be, you apply more fuel, temperature goes up, maintaining the temperature. So we deal with trying to maintain. We have a model of our process. We have some really simple learning in this controller that tries to maintain around an operating set point. And then after we maintain around a nominal operating set point, the temperature of a bake or the diameter of something that we're trying to extrude, then we throw the remaining variation to the other side of the process control, which is statistical process control, where we monitor, we assume that the world is normally distributed. We assume that there is still randomness. We're not going to be able to eliminate all variability. But we watch for the randomness, and we say that we're in a control state, a good control state from a statistical perspective, if our mean doesn't vary and the spread of our variation doesn't vary too much. And so what we can do with machine learning is start to bring these two worlds together. The SPC, that's big data. We don't have to assume that the world is normal. And, well, instead of having a line between those that are the practitioners of real-time feedback control and statistical process control, maybe we can bring those worlds together. And that's the story that I'll end with. That's what deep reinforcement learning as a mathematical architecture will allow us to do. So now let me just dive into a couple different cases. So first on machineware. Here is a packaging machine. Through this packaging machine, my bottles, or 6-packs or 12 packs of bottles, will come through this conveyance system. And there are a bunch of real-time controllers that are maintaining the position, the speed of this package of bottles that comes through this machine. The sensor, the data, these time series data, I don't have a mouse to point to, but the time series data, the wiggles over time, that is the torque versus time of a motor that's applying a blade to cutting a piece of plastic that's being wrapped around the bottles. We have position versus time, acceleration of both the bottles coming through, the plastic wrap that's being wrapped around. And on the right is the histogram of that time series data. We get all these time series for each package that comes through the conveyance. And the packaging system is doing its job. 6-pack comes through, 8-pack, 12-pack, out the other side comes a shrunk wrap package that's shipped off to the customer. Now the question that the manufacturer came to us with is, well, we do regular maintenance on this machine. So once a year, let's call it once a year, we go maintain the machine. We'll lubricate, add more oil, sharpen the blade, maybe change the blade. Sometimes the blade is still in a good state. Sometimes the blade is degraded. And I'm oversimplifying the problem here. But the question on the table was, well, can we actually get additional value out of the data that we have hanging out on the factory floor? Meaning, we have this data comes from the normal process of this machine doing packaging. Can we get additional value out of it? Can we actually look at this data and say something about the health and the quality of the machine? Right? So we have this data is coming from a real-time control system, controlling the positions of the bottles that are coming through, controlling the amount of torque that's being applied to a blade that's cutting plastic wrap. And for a moment, let's just, for simplicity, to oversimplify, let's just focus on the blade. So what's your physical intuition if I say, is there information about the health of the blade, the health of the cutting surface that's being attached to a motor that's going to be pushed through some plastic wrap that is wrapped around this package? Is there information about that aspect of the health of the machine in this data? So this data is coming, every 8 milliseconds a package comes through, moves the package around, wraps plastic wrap, cuts it. If I gave you a dull scissors, and I gave you a piece of plastic, it's going to take you a little bit more time and maybe a little more force or torque to cut through something than if I gave you a sharp scissors. And similarly, at minimum, we would expect sort of a physical intuition that if I have my blade and it's wearing, that I'm going to take a little bit more time and a little bit more force, torque, to cut through that. Right? So there's a physical intuition, the physical context. Yeah, there's probably some actionable information here. Now, what's the challenge, though? We don't want to add any sensors. We would like to just use this data. We don't want to have to add a sensor that's monitoring the quality of the blade or the amount of oil that's being used or the quality of the final product. All these are sensors that we could add. We don't want to have to do that. It's more cost than we want to bring to bear. So what we would like to do is have a model, a digital twin of this machine that takes this data as input and predicts the health of the machine, the age, the quality of the machine, how well is it mechanically operating, is it getting sick, and if it's getting sick, to then go to decide to do some maintenance. When you do machine learning, you would like to have your input data and some labeling to make sense of that data. So what's the labeling that we have of this data? Well, if, and this is a big if, it took a year to answer this if we also have, in addition to all this process data, if we also have the maintenance data, if we know the time since when we did the last maintenance, historically, if we have our maintenance data and our process data, and if, big if, that data is also in the same database. Now, in practice, that took a year. It took a year plus to get those data sources together. And that's sort of one of the big fundamental challenges. You don't need ChatGPT to make use of your data if you can't get your data temporally aligned. Right? So, but once you do that, once you say, hey, I have this maintenance historical data, the last 10,000 packages that I've made of all my process data, of all my maintenance data, and then I can put it into one of the simplest workhorse tools of machine learning. This is my graphical representation, for those of you that raised your hand around decision trees, support vector machines. A decision tree, if you know no other machine learning tool, it's a good first place to start. It basically looks at your historical data, say, well, what are the information-rich questions to ask and answer? It's like, is the torque above this level? Is the speed this level? And it helps you to make a series of questions that do the best that it can of mapping your input to your output. Your input and the output in this case is all your time series data that predicts the age of the blade since it was last maintained, because we're going to use age since maintenance as a surrogate for the wear. And once you do that, this is what a decision tree looks like on the real data. You actually use a bunch of decision trees to call them a random forest. You're able to get some results where you have now a virtual model that if you update it regularly, you make it a twin. And what do you do with a model? You would like to say, well, how well does it work? So let's take the data that we didn't use to train this decision tree and compare it as the ground truth to what our model predicts. And if the model is perfect, it should exactly predict what we know the real age, the real surrogate for wear to be. And so on this error versus time chart, what we'd like to see, now that we've used some historical data to make a model to predict the quality of the blade, and we have some examples where we know the quality of the blade, we compare them. If the difference is 0, our model is great. And from a machine learning perspective, I want 0 very close to 0. But here we see, well, we have 8 months of error, 10 months of error. So the model is predicting that it's 2 months old. In reality, it was 10 months old. That doesn't sound like a great model. Until we recognize, well, how are we really going to use this? It's unlikely that the age of the blade is going to change much from one package to the next. And what we have here is a noisy digital twin, a noisy model. And what would you do with a noisy sensor? You would apply signal processing. You would smooth it. You would do a moving average. Don't just look at the age of the blade after one package. Let's look at the last 200 packages and smooth that. And so bringing to bear the best practice of existing tools, classical signal processing and filtering, with the simplest of simple machine learning tools, a decision tree, allows you to have impact using the data that you have hanging out on the factory floor, but bringing together both sort of an understanding of the context and how you deploy tools, sensors. So I guess some of the points to make. The data engineering basics, getting your data aligned. Simple models, such as decision trees, are often very powerful. And even bad models, meaning a decision from a pure machine learning perspective, this decision tree gave significant errors on a per package basis, but when used in the appropriate way, the same way that you would use a sensor, gives you really good results. Okay, so that was story one. I'm going to accelerate the speed now. So digital twins, looking at now the manufacturing of engines. So we're going to sort of remind of this framework. Sort of have, on the one hand, we have real-time feedback control, on the other side, statistical process control. Anybody want to explain? Now, this is my sort of tutorial on neural nets. How would you explain to my 11-year-old child, or to your partner, or to your spouse, your grandparent even, how a neural net works? Right? A neural net is nothing much more complex than fitting a line. When you fit a line, this is machine learning. I looked at these red data. I applied a line. What the machine learning did was learn the right slope and intercept. It learned the right parameters to fit the mathematical structure that I picked a line to this data. The same is true when you are trying to fit data using a neural net. A neural net has a bunch more parameters. It has weights and biases and all these neurons that are connected together. But under the hood, we have a lot of data. We're fitting a line to our data. We're fitting a mathematical structure that I can't write down in closed form, and I need these things like backpropagation and iterative algorithms to find the weights and biases. But I can take a bunch of input-output data, X versus Y, and instead of fitting a line to it, I can fit a neural net to it. So a neural net is not anything more complex than fitting a curve to data. Now, that's the tool we're going to use. What's the application? This is what's called a variable compression ratio engine. It's sort of like an internal combustion engine with a little bit more complexity. and that the mechanical structure itself changes in order to change the compression ratio. VCRs have been around for a long time. They've only been manufactured recently. There's a company in Japan that has recently moved their production line to the US. That now gives you enough information to actually figure out who the company is. But we've worked with them to try to improve how they manufacture their variable compression rate engines and to not allow bad engines into the wild. I'm not going to go to the YouTube link here. You can go to that if you want to see some really interesting videos about how these engines work. This is the manufacturing process for this variable compression rate engine. It goes through some 30-odd steps. It starts with mechanical components that are at each station bolted together, locally inspected, goes to the next station, bolted again. And every engine has to be manufactured. And given the complexity of these engines, every single engine, of the first 50,000 of them that were manufactured, every single engine not only was manufactured, it was fully functionally tested. So we took the engine, collective we, not me, but the company, took the engine, put it on a shaker table, shake the engine, see how much it shakes in response to being put on a shaker table. Pressurize the engine and ask the question, how much torque is required to break static friction? So every engine has to be manufactured, but it's really, really expensive to have to functionally test every engine. So the question that they came to us with is, can we develop a virtual sensor, a digital twin, a model, that will predict the functional test from all the assembly data? So I'll go fast here, I'm seeing my time, but what's your physical intuition? If I don't bolt my engine down very well, it's going to shake and it's going to vibrate, and that's going to be really bad. If I have a big tolerance between, say, the side of the piston and the piston wall, it's not going to pressurize. So physically, yeah, I expect some connection between how the engine is assembled and its functional test. This is just some of the data that we use, the assembly data. We have torque versus time on all the bolts. This is some of the performance data of how it shakes. And so indeed, it is possible to use a neural net to take these several hundred parameters of all the production data, the assembly data, and predict various aspects of the functional test. And that's what's shown in this middle, the data training assembly test, a learned model, and we're showing just a small subsection of what the neural net is predicting for us. The functional test parameters as a function of the input parameters of assembly. Now, we did not yet, this is an ongoing project, we're not yet comfortable enough saying we're going to turn off the functional test. Right? So the way that we actually use this is, well, truly turning it into a twin. We're going to, on the bottom half, take the new assembly data, predict what the functional test is, compare the functional test, the shaker table, the pressurization, compare that to the new test, and then we've been able to use the difference between that predicted performance of how the engine shakes or how it pressurizes to what the actuality is, and then use that to bin the engines. Every engine is passing, but we've been able to identify which engines are going to be the super performers and which engines are just good enough. And now the exciting thing that we've been able to do is map that back, that variation, if we go back here for a moment, map that variation in the performance of the engine. Why are some engines super performers and some not? It depends on each engine, as it's being assembled, passes the quality gate at each station, but sometimes it's on the low side, sometimes it's on the high side. So an engine takes this complex path through the upper and lower bounds of the metrics that dictate quality on each stage. And depending on that path, you'll end up with these engines that are really, really good or just sufficient enough. And so now with this additional insight, we can go back into the manufacturing process and improve the process metrics as a function of how they flow. And so maybe from stage 1 to stage 2, we have to change the KPI for a second stage based on where it was on the prior stage. So the last story I'll tell you in a very short period of time is on optical fiber draw, where this is now, let me skip this slide for a moment. Okay, this is this architecture. So what I want to put this up here is, don't worry about the details, but what this is in the language of manufacturing, it's a mathematical way to think about jointly real-time feedback control, and statistical process control. Real-time feedback control is dealing with deterministic sources of error. And SPC looks at that long-term trends over time. What this mathematical structure does is, well, this piece looks like a real-time controller. And everything else here, all this other stuff, is the long-term memory. It's the stuff that we typically, in the manufacturing context, throw over the wall to the SPC, the statistical process control, assuming the world is normal. But here we've connected the two. Here we say, well, we're going to monitor those changes and trends over time, and we're going to automatically learn a model, have a twin, that feeds back into the thing that we use to do our real-time control. So the blue things here, that's a longer-term trend that's over having made hundreds and hundreds and hundreds of kilometers of optical fiber that is feeding back into the real-time aspect of this that is at the microsecond level doing variations of the machine to compensate for material variation, machine variation. Okay, so I'm seeing I'm rapidly clocking out of time. This is the paper that you'll have access to is just sort of talking about the detail of how we demonstrated both in the lab and on the factory floor. Lots of challenges to deploy this on the factory floor. To be able to use a singular control architecture, digital twins, models over time, that bring together these typically disparate halves of the manufacturing ecosystem for control. Real-time control at the sub-second level and statistical process control, and eliminating the barrier between those two practices. And with that, I'll take some questions.
Brian. Yeah. Okay. How can manufacturers empower their workforce to co-evolve with AI and automation, turning operators into data-driven decision makers and engineers into system designers rather than system fixers?
Yeah. No, awesome question. So, one of the challenges with deploying machine learning onto the factory floor is you need it to meet the workers where they are. They understand manufacturing processes. You understand the machine. So the tool has to be deployable. So putting it into context, in my experience, putting it into the language that they're familiar with, putting it into the language of feedback control, of, well, I measure something and I adjust something. Okay, that's a model. So we can do something better and more innovative than PID. So not breaking the understanding that they have, starting them with the processes that they follow, and demystifying a little bit the magic of the names of the new tools into something that they know. And then, by all means, I didn't emphasize it enough, to be successful in this domain, you need to bring to bear an understanding of the physical issues, an intuition there to have an intuition that the models, that machine learning is going to be able to extract some relevant physical data, information from the data you have. And so that journey of empowering the workers, like you know a lot more, you know the physical context, you know the complex interplays that you have to teach, help the algorithm or the tools use, is sort of one of the secrets.
Okay. Next question is, are you exploring physics-informed neural networks for engine predictive maintenance and integral physical laws into your machine learning models?
Short answer, yes. So there, in this architecture of neural nets, to pick on that for example, you can embed aspects of the mathematical structure, the way that you expect. If you write down F equals MA, and have understanding of the physics of your process, whether it be for engine manufacturing or other, you can incorporate that baseline structure into your learning tools and not have something that's a generic line, right? But have something that is the right structure that's informed by your physics, and then learning the parameters. So knowing the right mathematical structure is sort of where the physical intuition comes in, and then using the data to identify and fit to the parameters that capture that underlying structure.
Okay. Most examples use time series signals. Have you seen success predicting wear or quality using mostly other logging types and configuration data? If so, what features tend to matter most?
Right. So actually on the engine example, to keep this parenthetically, on the engine example, yeah, we have a lot of time series data, But each station there's high-level logs and configuration, so it's not all time series data. Maybe reread this. Have you seen success predicting wear quality using mostly other logging types of configuration data? So I guess the one that I would point to, not maybe completely understanding the question, is in any of the stations, for example, in the manufacture of the engine, there are lots of different configurations, and not just time series data. There's the observational data that the operator will make. There are set points on how the different tools are being used. So in the interest of time, I dramatically oversimplified the story I told, but it's certainly, yes, time series data is very important, but configuration and log data. And then also, these maybe some of the examples sort of more biased toward looking at individual processes, but then when you think about a system, the manufacturing system, a factory, where it's process 1, process 2, and process 3, now we can start to think about applying machine learning tools the same way that we think about how we analyze equipment efficiency. So if we look about the mean time to failure, mean time to repair of processes. And classically, the way that a manufacturing system is analyzed and modeled is, well, let's look at the aggregate amount of time that a machine is up or down. And so that's a high-level statistic. And so those are things that you can learn how to appropriately sort of design your buffers between machines, or whether or not you should invest in a new machine. But some of the innovations that we're seeing now are bringing together things like discrete event and discrete time simulation to improve factory flow at the mean time to fail, mean time to repair level, with more intimate knowledge of what's happening at individual processes.
Okay, thank you, Brian. For the sake of time, I think we should stop here. Again, we're going to have a coffee break so you can ask more questions to Brian. Thank you, Brian.
Thank you.
The next session is a fireside chat moderated by Vincent Maret, Group Bouygues Innovation and Transformation Director.
Jérôme. Well, thank you, Juan. First of all, thank you for lending us your New England treehouse. The definition of a treehouse in Massachusetts is you can put the tree in the fireplace. So we've just heard from Niels Fonstad of MIT Sloan on how trailblazing firms are turning uncertainty into growth, and from Brian Anthony from MechE on bridging the physical and virtual worlds through digital twins. But let's now shift to a more traditional construction close to our hearts, the construction industry, and come with concrete examples from Bouygues Construction and their use of Omniverse from NVIDIA. I'm Vince, and I will be conducting this chat. And I'm joined by JEROME LOYWICK, R&D and Innovation Project Manager at Bouygues Construction. Jérôme is leading the exploration of NVIDIA Omniverse, a collaborative simulation platform that's helping Bouygues rethink how teams design, coordinate, and build. But Jérôme, let's start with the basics. Omniverse, it vaguely sounds like metaverse. Not such a good sign for concrete help on real project. What is it really, and why did you select Omniverse among the gazillion choices available to you?
Yeah, you're right. Omniverse vaguely sounds like metaverse or other shiny concepts, but for Bouygues Construction, it was never about chasing new trends. It was about finding the real value for our project. And when I started to work on digital twins project, I conducted a technology watch to identify the different players in the field. And we ended up with 6 main categories, from data pure player to software from other industries. And NVIDIA was alone in one of these categories as a GPU pure player. GPU stands for Graphic Processing Unit. And it was really interesting for us because NVIDIA is more than a software company. NVIDIA can bring AI expertise, real-time graphics, and simulation, and Omniverse merge these two worlds together. Omniverse, what is it? It's an open platform. It connects tools, people, and data in the same world. And it allows our team to collaborate in the same digital space. And it's a kind of disaggregated API platform.
Thank you very much. And it's all about people, as Niels mentioned. Can you share how Omniverse makes a difference in the real world on our project, on your projects, on a site, in a design phase, or in coordination situations?
One of the key reasons Omniverse makes such a difference is the technology it's built on. It's OpenUSD. USD stands for Universal Scene Description, and it's more than a file format. It's an ecosystem initially created by Pixar Animation Studio to tackle the challenge of connect different tools in the same ecosystem, whatever the file format they use. So now OpenUSD is open source, and it's something created initially for animation movie, but now it's growing in other industries, like, for example, automotive, manufacturing, and also robotics. And OpenUSD is a standardized way to exchange 3D data. And Gabriel from NVIDIA will probably give you more details about that, because it's also enabled physical AI in Omniverse. And yeah, it's a way to connect tools, people, and data in Omniverse. And in traditional 3D processes in construction, data tends to be hard to update and hard to share because it's really monolithic. And OpenUSD completely changed the game with Omniverse.
Wow, so Pixar, digital, for those of us who are going on the site sometimes, it's an entirely new ballpark. So what first reactions did you get from your teams on the ground when you pitched Omniverse internally?
Yeah, the first reaction of the people was, wow, they are really impressed of the realism of the 3D scenes. And then they understand the endless possibilities of Omniverse, because we can connect almost everything, different tools, different type of data. So yeah, there is many possibilities with Omniverse, and our projects are all different. And the challenges are different, and Omniverse is really versatile. So, yeah.
We love solving problems, Niels, at Bouygues. So how does Omniverse connect with digital twins and AI? Are we talking about predictive modeling, real-time simulation, or something else? Can we get inspirations from other industries like Brian showed us?
What's really interesting in Omniverse is that we are not alone exploring it. There is other companies, other major players, like, for example, in automotive, BMW and Mercedes are creating digital factories in Omniverse. In logistics, companies like Amazon or Keynote are simulating warehouse operations.
What is Keynote?
It's an American logistic company. In Taiwan, there is also Foxconn, a manufacturing microcomponent company, simulate the robot in a virtual environment in Omniverse. But also in France, there is French companies like SNCF and Saint-Gobain are using Omniverse in the same way. So it really shows how versatile the platform can be. And at Bouygues Construction, we take a step-by-step approach. And we want to be sure that every use case is connected with real projects and real needs of the company.
So we see it's working well on the ground. So Jensen Huang mentioned Bouygues. Can you believe that? As pioneer user, what a success. And now, what are your plans to bring Omniverse on site Who will be involved? Engineers, architects, site managers? How will they interact practically with these new tools?
Yeah, I think that Bouygues Construction always plays a pioneering role by using new technologies for the project. And last June at NVIDIA GTC in Paris, Jensen Huang mentioned Bouygues Construction as the first general contractor using Omniverse, exploring Omniverse. And it was a great moment for us because it showcased, to see our work recognized at this level. And I am also really happy to work on this project. And now the next step is to bring Omniverse on the construction site for our project. Deploy Omniverse in real project. And in design stage, Omniverse can help engineers to simulate different scenarios and think about the way we will plan and organize the construction site. And in construction stage, Omniverse will help us to compare the performance of the construction site with the simulations. And it also opens new opportunities with our clients to change the way we collaborate together, and why not deliver USD file of their factory compatible with Omniverse to create digital twins in the future.
Well, so thank you very much. And looking ahead, what's next for Bouygues Construction in this space? What breakthrough could redefine how we build, the way we build, the process? Can Omniverse help us anticipate better our projects and their realization?
At Bouygues Construction, in our R&D and innovation department, our first commitment is to be a business partner. So my goal is to help teams design and deliver complex projects more efficiently. And I think Omniverse can be a really powerful simulation environment and to plan and organize, and my ambition is to equip our project with the best technologies. So yeah, that's the way the path we're taking with OpenUSD and Omniverse.
Well, Jerome, thanks you so much for taking us behind the scenes at Bouygues Construction and showing how digital innovation is transforming construction at Bouygues as we speak. Looking forward to seeing where Omniverse leads us next. Juan, the stage is yours for the rest of the meeting.